class. Today we're going to be doing section 2.7 for AP Stats. We're going to be looking at the line of best fit, or the least squares regression line for linear regression. We're also going to be looking at some mini-tab outputs and the conditions that need to be met for doing regression, for linear regression. So we're going to start really quick with a definition of the line of best fit. So the line of best fit minimizes the cumulative vertical distances between each observation and the line itself. So in my colored pen here, they're talking about these distances here. So if I go from each point to the line, straight down or straight up, those cumulative, so if I add all those distances together, the line that minimizes that amount is going to be our least, our line of best fit. By the way, those vertical distances are the residuals, so we call them the residuals. And a positive residual are for points above the line. Negative residuals are for points below the line. This is also known as the least squares regression line. And oops, that's not what I wanted to do. Let me get the regular pen here. So we call that LSLR, least squares regression line. Oops, that's not LSRL, least squares regression line, which I'll abbreviate from now on. And we call it the least squares because if you take and make squares out of those residuals like this, and you make a square for each one of those points, it's the line that minimizes the sum of those squared residuals. So kind of a little bit more complicated, but it has the same idea. All right, so I'm going to jump around these notes a little bit. I'm going to let you go into the calendar for our course and fill in all the rest of the notes that I'm not going over on the video today. So we're going to skip to the second page for example 2 here. And we are going to be using our graphing calculators. So studies have shown that people who suffer sudden cardiac arrest, or SCA, have a better chance of survival if a defibrillator shock is administered soon after the cardiac arrest. How is survival rate related to the time between cardiac arrest when it occurs and when the defibrillator shock is delivered? Sorry, it's early in the morning for me. All right, so the first thing we want to do in our graphing calculator is go to Stat and Edit, and then put these two lists into your lists for your stat lists here, which I've already done. And we're going to use L1 as our X and L2 as our Y. If you're not sure why that's X and Y, you can go look at my 2.6 video where I discussed explanatory and response variables. So now finding X bar, which is the mean of X, and Y bar, which is the mean of Y, I want to use two var stats. So what we're going to do in our calculator is go to Stat, and then over to Calc, and then down to two var stats. Hit Enter. My X list is in L1, my Y list is in L2. I'm going to go down to Calculate, and there is my X bar at the top. So X bar is 7.2, and then X is min call to shock time in minutes. And our Y bar is down, and if you see, I can actually scroll down. There's a lot of information in these two bar stats, but Y bar is there. It's 34.4, and that's going to be survival rate. So that's percentage for survival rate. Survival rate. All right, and then we're going to find and interpret the Pearson correlation coefficient. So that's our linear correlation coefficient, or R. So for that, we want to run a linear regression. So we're going to go back to Stat, over to Calc, and then I always go down to the 8th one here on my calculator, which is Lin Reg A plus BX, because that's the one our book uses. And there's the 4th one, it'll do the same thing for you. So I'm going to enter that. And I have L1, L2, and I'm going to go down to Calculate. And here I have my R value. So R is negative 0.96. And then interpreting that R value, in the 2.6 lesson, we talked about that a little bit. So you can go back and watch that again if needed. But there exists a strong, so we talk about strength. it's negative. We talk about direction, negative, and it's a linear regression. So it's going to be the form is linear here. So strong negative linear relation between the mean call to shock time and the survival rate of an SCA sufferer. So always make sure to include a lot of that context in there. Find the regression equation for the association. So we have our regression equation in front of us here. When I write that, a couple new things. I'm not just going to write y equals. I'm going to write y hat equals. And y hat is the predicted survival rate. So it's really important that we note that our least squares regression line isn't going to give us the exact y values. It doesn't actually go through any of the data points we have, but it'll give us predicted y values based on x, which was our mean call to shock time. If you forget to define your variables, that might cause you some points, so loss of points on the AP exam. So make sure you define your variables. So y hat equals, and then my a value is 101.328. Minus b is 9.296x. All right, so there's our linear regression equation. And then what is the predicted survival rate when it takes 5 minutes for a shock? So y hat is going to be this here minus 9.296 times 5. So this is just a basic substitution problem. And that ends up being 54.848%. And then what is the residual for a value of 7 minutes? So I kind of mentioned this at the beginning of the video. The residual is going to be our y value, or the y value of the actual data point that we have, minus the predicted value. It's going to be positive for points above the line and negative for points below the line, which is how I always remember which direction to put the y in the y hat. So if I have a 7-minute mean call to shock time, I'm going to figure out what is the predicted value for that. So I'm going to plug this in, 296 times 7, and I get 36.256%. And then if we look back up at our data, it was actually 30% in real life here. So versus y was 30%. So now our residual is going to be 30 minus 36.256. So if you picture the line and the y hat is the point on the line, our y value is below that. So it's going to be a negative residual. And then that's going to be a negative 6.256% residual. It's only percentage because our units for y are percents. So that's why I have percentages there. All right, again, I'm going to skip a little bit because this video is going to get too long if I don't. So you can go to our calendar and fill in the rest of that page. On the next page here, I'm just quickly going to go over mini tab output. So you're going to see these on the AP exam a lot. Pretty much it's like we don't have to use our calculator. They're doing the calculator part for us. We just had to interpret pieces. I've highlighted the parts that we're going to use. There are some green parts that I highlighted that we're going to use later when we do inference, but for right now, those aren't going to matter. Only the yellow highlighted parts are what we're using today. And I'm going to use the interpreting again for, you can copy those in the notes later. So writing the least squares regression line from here, remember the constant term, this is the term without the variable. So that's going to be like our a value in our equation. So y hat equals our constant term 44.540, and then plus our coefficient for the predictor value of revision time. So that's going to be our slope, 0.55528x. And then again, we need to define those pieces. So y hat is predicted revision time, exam score versus revision time. Actually, I think it's predicted exam score. I think my notes are wrong here. And x is revision time. I could have that backwards. I apologize if that's backwards. My notes are a little backwards right now. Okay. And then the coefficient of determination. So this is r squared defined in our notes earlier. This is here. We've got 72.8%. And then you can look at the notes for the interpretation there. It's kind of lengthy. And the correlation coefficient is r. So what we would do is we would square root r squared to get r. So we'll square root 0.728, and then that should end up being 0.853. So you have r, you just have to do a quick calculation to get it. Okay, next page. So this is our day 2 lesson here, but I'm just gonna try to fit it all in one video. We have conditions for the appropriateness of a linear regression model. So we can't just jump into linear regression. We need to check to make sure that it's an appropriate thing to use. So I'm going to go and I clear my calculator here because we don't need that right now. So we have a few conditions. The first one is that both variables must be quantitative, so not categorical. The second one, the data, either original or transformed, we'll look at transformations later, has to be reasonably linear. We want to draw the scatter plot to make sure that we can prove that it's reasonably linear. We also want to check that the residual plot displays no obvious pattern, that it's pretty random. And I would suggest also drawing your residual plot because we want to be able to talk about both of those things. The third part is that the variability of the residual should be constant. So we shouldn't have like a fanning out of our points from the line. You can kind of see that example here. This is a bad thing here. We want it to be a constant spread of the residuals. And we can talk about that based on the scatter plot and the residual plot that we drew previously. And then the last one is that there's no influential observations or outliers. An influential observation is a data point whose x value is far from the mean of x. And those points are going to be also, so there's outliers, there's influential observations, and high leverage points. And they're slightly all different from each other, but pretty much you're looking for if there's a point that is far away from the mean of x, so kind of on the ends, and not in line with the rest of your points, and it's probably like tilting or kind of spinning, pulling that line towards it when it shouldn't be. That's what we're looking for. So we don't want any of those. And if there are any of those, we can remove them from our data. But we do need to make a note that this point did exist and we've removed it because it didn't fit our conditions. All right, so now let's look at an example. Example 1 here, we'll kind of do this whole thing here. So we have the data below compares the height in inches and weight in pounds for American females aged 30 to 39. So we have X is height, Y is weight, and they told us that in the problem, which is nice. The first thing you want to do is go into your stat, edit, and then I put the list in L. Oops, I lost my L3. I can get that back later. But L4 and L5 in this case. If you ever lose a list, just let me know and I can help you put that back in. So we want to find the correlation coefficient, the coefficient of determination, and the least squares regression line. So we're going to do stat. We're going to go over to calc and go down to the 8th one here, which is linear regression, A plus BX. My data is in L4 and L5, so I need to update that here. I'm also going to store my regression equation because I'm going to get my scatter plot in a second. So I'm going to go to vars, over to yvars. The first one is function and y1. And then that way it'll be in there for me. So here's all the information I need for part A. So y hat is going to be negative 99.057 plus 3.61x. And again, we need to define those variables. X is height in inches, and y hat is predicted. It's important you put that, weight in pounds. Okay, our r squared and r, so r is our correlation coefficient, is 0.994, seems strong, and r squared is 0.989. So again, one of the cool things about this example, and you'll see in a second, is that it seems like everything's fine. The r and our r squared are really strong, so it seems like this should be something we're allowed to use. but it's not going to end up being appropriate to use a least squares regression line as our model. And that's why it's so important to check all the conditions. So now we're going to sketch the scatter plot and the residual plot, and then think about all those conditions. So to get our scatter plots and our residual plots, the first thing you're going to go is second, and then the y equals up to stat plots. I like to leave my first stat plot for things like box plots and histograms. So I'm going to go down to plot 2, and I'm going to turn this on. And I'm going to make sure that my other plots, I'm going to go back here. I'm going to make sure my other plots are off. So it looks like my plot 3 is on. So I'm going to go into that and turn it off. We'll use that in a second. So now back up to plot 2. And my data again, so I've got on, I have my scatter plots, the first one. My data is in L4 and L5. So I need to fix that. And then I'm going to go to zoom. And the 9th one is stat. So zoom stat. Now, if you look at this, I mean, the points are actually touching our line, which is really cool. And it looks linear. So far, it seems like everything's checking out. I want to sketch this line really quick here, and I want to draw my points as well as I can. They don't have to be perfect. I always draw my line first, and that helps me kind of get a decent picture of what's happening. Okay, so I have that. And then I want my residual plot. So now for this one, you're going to go back to our stat plots. I'm going to turn off this one. And then I'm going to go to plot 3. So I'm not changing my plot 2 to residual plot. I'm keeping it the way it is. I'm making plot 3 my residual plot. I'm going to turn it on. I need to go to L4 for my X list. And then to get this to say residual, what you want to do is go second stat. So to your list, and then it's the 7th one down, residual, and then that'll put that in there for you. Now, it already calculated all the residuals when we ran the linear regression calculation. So the very first thing we did to get our line and our R and our R squared, that's what made all of the rest of this happen. So you have to do that first before trying to graph these. All right, and then I'm going to go to zoom and stats. And if you notice, our residual plot definitely does not look like a random shape. It has a curved pattern, which is bad. And now that we see this, and I'm going to sketch it because we're going to reference it, so we definitely need it drawn on our papers. Now that we see this shape, if you look back at our scatter plot, you can kind of see that the point started above the line and then kind of went below the line and then back above the line. And that's what this is making more clear, which is why it's important to check all your conditions, because everything seemed like it would be okay, but it's not. Maybe a quadratic or an exponential model would have been more appropriate than a linear model here. So determine if the least squares regression line is an appropriate predictor between height and weight among these females. It is not appropriate to use this to predict the weight of an American female aged 30 to 39 given her height, because the residual plot does not appear random. It has a curved pattern. So make sure everything's in there. Everything else checked out, but that residual plot condition definitely did not. All right, and then let me just double check. I think that was it for our notes for today. Make sure to check the calendar for the rest of those notes and get them filled in.